All right. Well, I will try to not prevent you guys from getting to lunch ASAP if you start to get hungry. So we're going to be talking about some tales of Android browser exploitation. My name is Ben Watson, and I go by Logics on the interwebs. I'm the co-founder of a mobile security research initiative called Lifelong Labs. I'm also the creator of Lobotomy, which is an Android reverse engineering toolkit, and that is freely available on GitHub for your downloading and viewing pleasure. And obviously, here are my Twitter handles, and you can follow me so I can lurk on you. So today's agenda, I'm going to be going over some of the motivation that I have personally for just doing a whole bunch of vulnerability research around Android web browsers. We'll look into some of the vulnerability classes that I kind of used to present the output of that research that have kind of always existed. We'll look at how to analyze the attack surface of a given Android web browser, and then we'll go through two exploitation tales. One is for the Dolphin browser, and the other one is for the Mercury browser. I dropped all that stuff late last year, and there's been demos out there and whatnot, but this is kind of the culmination of all the research and the perfect storm of when you can chain a whole bunch of stuff together and get code execution. So why are Android browsers so attractive for exploitation and vulnerability research in general? I would say when I started digging through the Google Play Store to find new classes of apps to research, Android browsers really kind of caught my eye because of the large numbers of user installs that they tend to boast. Now obviously you have Firefox and Chrome, and those are very popular, not just on Android, but on cross-platforms in general. But if you check out the Dolphin browser, and this is, or could be considered to be an alternative browser to a Firefox or a Chrome, it also boasts some pretty significant numbers. In general, my idea was, all right, well, if I find some type of code execution bug in a popular browser, then in general, the impact to that user base is pretty good. Android browsers in general, they also request very excessive permissions, and that's usually to support, especially in the alternative browsers, a lot of different features that they have. Now, if you're able to execute code inside the context of a browser that's requested a lot of permissions, well, that's very fruitful in terms of post-exploitation. In general, what you're able to get access to from a data perspective. Here is a snippet of the Dolphin web browser for Android's permissions. This is just, it literally is just a snippet because this is not all of them. The Dolphin browser wants to have access to your accounts, credentials, right to external storage, Wi-Fi state, network state, etc. What's really interesting is if you look at the amount of permissions that browsers, specifically these alternative browsers, request, and then Android malware, they're very similar in the amount that they request in terms of what they want to have access to and what they want to be able to do. Android browsers are often taught with features, not necessarily the Chromes and the Firefoxes of the world, but the alternative ones. They always have something that makes them better than their competitors. In general, this builds and saturates the overall attack surface of the browser, and then also, and what we'll kind of demonstrate today, is it builds very solid remote attack vectors. So some of these features could be custom URL schemes, it could be Flash or HTML5 video support. So this browser that I'm still currently looking at, it implements a custom file manager. So if you download a 7-zip file, it says, hey, I want to be able to support that, and so I'm going to write a shared library and natively parse 7-zip files and extract the contents or whatever. And you will see this all the time. A lot of the alternative browsers do things like that, like have file managers where you can manipulate the stuff that you're downloading through that particular browser. Other things like configuration updates, you would assume when an application checks to see that it's not its current version, it would put you to the Google Play Store where you can safely download that application, etc. Well, a lot of these browsers, not only do they update themselves in terms of the app as a whole, but maybe they pull down additional configuration updates for their features. And typically they go through their own communication channels to do that. such as downloading executable files, jars, etc. over HTTP, which can obviously be very easily man in the middle. Other things like third-party services integration. Why wouldn't you want to integrate Dropbox, Facebook, Twitter, Instagram, all of these things into your browser? They also provide things like, well, if you break your phone and then you get a new phone and you install that browser, well, you should be able to back up all of your bookmarks history or whatever. Some of these browsers have their own custom cloud storage implementation, so you can back your stuff up there and then reload it after you're done. That's all implemented in very traditional web services, architecture, or whatever, and they are pretty taught as well with vulnerabilities. So some of the vulnerability classes that we'll be talking about, and these are by no means anything that I particularly came up with. These are just kind of things to describe the vulnerabilities that I think are really interesting in Android web browsers. The first one is going to be talking about insecure URI scheme parsing. Now, this could apply to any URI, such as a custom URI or anything that meets that RFC standard, but specifically we'll be talking about the intent URI scheme, which is very specific to Android itself. We'll be looking at the unsafe use of zip input stream. So this is specifically a class that is used to extract the contents of a zip archive. The inherent insecurity of using the zip input stream class to do such operations, and why Android browsers are using zip archives in the first place. We'll talk about writable code. This is specifically around the use of creating shared libraries in C and C++ in Android, and the fact that a lot of the browsers that I look at specifically don't use the traditional mechanisms of doing that and place that writable code in locations that are non-traditional, which can lead to becoming targets for arbitrary write primitives. And then general, we weren't going to be talking about anything fancy with transport layer protection. I'm literally just going to say there is none. Literally, there's none. So no SSL, no TLS, no nothing. Everything is primarily done over HTTP, and like the most insecure operations you can imagine, like downloading executable code, is done in that way. And the whole point of each one of these exploitation tales is to honestly just highlight how all this stuff can be combined into this perfect storm to achieve complete browser compromise. In this instance, we're talking about actually getting arbitrary code execution. So a quick refresher before we jump into the first vulnerability class. For those who aren't aware, the Android intent is a high-level inter-process communication abstraction object. It is implemented in Java and it's provided to developers. It allows communication between application components. Now, when I talk about application components in Android, that's an activity of service, a broadcast receiver, and also the content providers. But in the context of this talk, we're going to be talking specifically about activities. So each component has a corresponding method that can be used for invocation. You have start activity for activities, send broadcast for broadcast receivers, and then start services for services. The intent object structure includes two important properties, the action and the data property. The action instructs the receiving component, in this case an activity, to do something with that data. Here is a good example of an intent action, and this is what we'll be covering about how to abuse in this particular vulnerability class. So abusing the intent URI scheme. I would say that for the most part, some people understand what this is and know about it, but from maybe a developer's context, for these guys building these browsers, they may understand what it is, but they have no idea how to handle it whatsoever. So a little known feature in Android lets you launch apps directly from a web page via an Android intent. Now, when I say launch apps, I mean and invoke an activity. Activities in Android are primarily used specifically to handle all of the UI interactions with an application. So the intent URI scheme, it gives you the ability to create an intent object when it's parsed. So if you look at the URI scheme here, you can see that it's broken down into a couple different attributes, action, category, component, etc. Each one of these attributes, they are attributes of the intent object itself. So whenever the parse operations occurs, it breaks apart the URI scheme itself, and it goes through and takes each one of these attributes and their values, and then creates an intent object from that. The only other attribute that is not included here in the example is intent extras. So intent extras are just key value pairs that are wrapped up inside of a serialized object and it's thrown on the intent itself. So if I have activity A and activity B, activity A can send an intent, drop, first name, Ben. And an intent extra, send it over to activity B. Activity B can pull that out and access the first name and its value. So the component here specifically, when we talk about the activity itself, we're talking about the Java class that implements this. So the intent URI scheme here is literally just broken out the way that when it's parsed, it needs to be consumed in order to produce an intent. So parsing the intent URI scheme is accomplished through a static method that is a part of the intent class called parse URI. It takes the URI as its first argument, and then it returns a fresh intent object after it walks through its parse operations. So you can dive into the code, and you can literally see how it takes the scheme, and it has a bunch of identifiers, and it understands how to return that intent object. So support for the intent URI scheme, it requires handling it inside of the web view. We're talking about Android browsers. We'll be talking about web views, which is how you implement that, and the core foundation of creating a browser in Android. The intent URI scheme is not handled by default in any way, shape, or form. So if you're looking at an Android browser and you see that the intent scheme is being handled, it's because the developer made a conscious decision to do so. And we'll see how, for the most part, that's done pretty insecurely. So a common pattern in Android browsers is to override this method called should override URL loading. This essentially gives the browser inside of the WebView client the ability to take control over the URL that is actually assigned to the property, the JavaScript property of location.ref, before it's actually reloaded into another web view. So inside of this method is typically where you handle all scheme parsing, whether that's a custom scheme, file, HTTP, etc. But often the pattern is, if I've gotten the intent URI scheme, handle it here and do some stuff with it. So the intent, the insecure parsing of the intent URI scheme, it's not the parse URI method. There's not something insecure about the way that that method walks through its operations of generating a new intent. It's specifically what happens to that intent after it's returned and then it's passed to a method like start activity or a start activity result. So an HTML page was loaded inside of a web view. We have a scheme. That scheme created an intent object or an inter-process communication object. That is effectively tainted and untrusted data. So if you take that object and you pass it to a method that is designed to invoke something that handles inter-process communication, that is really where the vulnerability lies. So both start activity and start activity for result, they take that intent object as their first argument, and then as we've seen in the URI scheme, it takes the component that was set on top of that and then tries to invoke that from the intent object itself. So this is kind of what you have. You're in your phone, you're in your browser, you go to some attacker-controlled HTML, we've got a JavaScript. In the location.ref property, we have our intent URI scheme. That gets loaded. Should override URL loading has been overridden. That's where the scheme gets handled. The URI scheme gets passed as the first argument of parse URI. We take that intent object and we pass it as the first argument to start activity. And effectively, if there has been no sanitization of that object, then the attacker controls the component. So statically, you can look at that. You can disassemble and walk through the text and figure it out pretty quickly. But dynamically, there's a really, really easy way to just automatically figure out whether or not this URI handling pattern exists and whether or not you have a vulnerable browser. So we need to do two things. First, we need to craft our HTML with an intent URI, not specify a component and only specify an action. The second thing we do is we can use this new attribute called a selector and attach that inside of the URI. And literally what that says is, if I have a selector intent and I have a main intent, then the selector intent And that component assigned to that is what is used as the component resolution, or what do I need to resolve the activity on the other end of the operation. So what that essentially does is it bypasses any type of component nullification or just assigning the component to null or reassignments. So sometimes developers say, I may or may not understand how this works. So if I get an intent object, I want to assign the component to null and then pass it to a start activity. This doesn't make any sense to me in general, but I see it all the time. If you attach a selector attribute to it, it tells the component resolution process to look at the selector intent outside of the main intent. So when you access the component from the main intent and not the selector, and you set it to null, it doesn't do anything. The selector attribute bypasses that. So effectively, we can do two things. We can bypass any protections and then ultimately make sure that the component is set to null, because we want to ultimately invoke an implicit intent. So you can see here in the example, this is a very quick and dirty way of triggering this vulnerable pattern. So the intent object doesn't have a component assigned to it, and then it gets passed to a start activity. That means that we ultimately have an implicit intent. So an implicit intent is an intent object without a component. An explicit intent is an object with an intent object with a component, but we want to invoke an implicit intent. So if the activity manager gets an implicit intent, essentially this whole resolution process kicks in. It goes through and it says, hey, I've got an intent and I don't have a component. I don't know where to send it to, but I've got an action. So it goes through and it enumerates all the applications that are on the phone that have exported activities, i.e. they're public and they can be invoked by other applications on the phone. It goes through all those exported activities and it looks at the intent actions themselves and says, okay, yes, these are all the ones that match with the action that I got from the intent that I don't know what to do with. And then it presents you this option. It says complete action using. I'm sure if you have Android phones, you have probably seen this in your lifetime of owning that phone. This is an implicit intent. Sometimes it happens on purpose. Sometimes it doesn't happen on purpose. So if we get this whole implicit intent resolution process by parsing our HTML with our URI scheme, this means that we have a vulnerable browser. And if we've used the selector attribute, it also means that we were able to initially bypass any haphazard protections that were done. We're good to go. All right, so effectively now we have the ability through HTML, when it's loaded into a browser, to create an arbitrary intent object. And what we want to do is we actually want to invoke private activities within the browser, but we could also invoke exported activities in other applications on the phone. I like to call this like an inter-process communication gateway for activities. So effectively, a private activity is an activity that's been registered on the application that says, only things that are inside of my app can talk to me. If it's public or if it's exported, it says that, well, other apps on the phone, they can invoke me. So effectively, because we have bypassed and broken this whole access control model, we can now target activities that the developer has not made public on the phone, and they've probably made a lot of decisions based off of this overall trust model not to sanitize any of the intents that have come in or check on those operations or anything like that. So we do need some additional primitives for an overall exploitation context. So what we really want to do is, because we can control the intent extras that are sent to, let's say, this private activity, we want this intent extras to be operated on in a way that provides us more access or an execution context within another activity that's implemented in a web view. All right, so the same scenario exists, but now we want to add an intent extra. All right, and the intent extra effectively would look like this. So we're trying to target a private activity that will load this intent extra as the first argument to a load URL call. So effectively, we can load arbitrary data inside of a web view. It's pretty straightforward to look at what activities are private, and then it's pretty straightforward to go through and actually look at how those activities handle their intent extras and whether or not one of those values is passed to a load URL call as the first argument. And then effectively always remember that if you can bypass any type of checks inside of the should override URL loading, that means you can control the component. So we are only talking about this concept of taking that argument, passing it to load URL, but you can effectively target any activity, and I don't know, whatever the activity wants to do with that intent extra, it may or may not be sensitive, but you can also target that as well. So private activities with implemented web views that take an intent extra and pass it as an argument to a load URL are cool. Now, if they do all of that, plus they enable JavaScript and file access, that is really, really key. So you're probably asking yourself, that's a lot to line up. Do those primitives exist? And yeah, they do. They're there all the time. Look at a browser right now. For the most part, you can find a private activity that implements a web view, and you can control it in this way. So we also care about methods like load data and load data with base URL. So the way that they handle paths and build them, etc., often really result in directory traversal vulnerabilities. And these two methods specifically, they present more control over the data type of that particular URL when it's loaded into a web view. So two example methods here, set allow file access and set JavaScript enabled. This is done in the web view settings. Pretty self-explanatory, enable or disable file access, which can be used with the file scheme, and then also enable JavaScript. And I honestly have never seen these primitives line up where JavaScript wasn't enabled on some arbitrary web view. So all these primitives, when they're combined, they can result in universal XSS, cookie theft, phishing, data leakage. I could probably spend an entire hour about all the different ways to exploit this particular bug and all the things and scenarios that you would need in order to make it happen. But we'll talk about this exploitation technique specifically. So one of the things that you can do inside of that HTML page that you control, it gets loaded up into the browser, is injecting arbitrary JavaScript inside of the cookies database. So you can do that simply with using a document.cookie inside of your arbitrary JavaScript, and then inject something like that inside of the cookies database. The second piece is, you would already know that you have a private activity where you can control the intent extra value that gets passed to a load URL call. So you use the file scheme in order to point the cookies database to the load URL call. So if the web view actually intends to open a SQLite database as HTML, then your end goal here is to get the JavaScript to execute, and then vicariously you can exfiltrate all of the cookie content, including HTTP only stuff. This is not very common with load URL stuff, but it's also very common with load data with base URL, because often you will see as an argument specified to one of those methods, the meme type there is hard-coded. And I'll show you an example of that. So the meme type is text HTML, then you have more reliability to get your JavaScript to execute and start your cookie data exfiltration process. All these browsers are vulnerable. Some of them I've talked about in the past. Some of them are unique to this conference. Now they all have the intent URI scheme abuse. Most of them have the necessary primitives you need for exfil. Some of them don't, but pretty much all of them, you can take that snippet of HTML, load them into the browser, and you'll see the implicit intent happen, and you know that you're good to go. And then from there, it's just figuring out all the additional things that you need for exploitation. All right, so on to unsafe use of zip input streams. So this has been around for a while, but to catch everybody up, so the zip input stream class is provided to you in Java, and it's also provided to you in Android. It basically says, if you want to handle a zip archive and extract the contents of the zip archive, well, this is the class to do it. The thing that's very unique about these zip input stream classes provided to you is its inherent nature to follow path traversals inside of the entries names and write data to that location. So if you go to Stack Overflow right now and you just start looking up like how to use zip input stream, every example is pretty much vulnerable. And it's really funny. It's like a systemic issue just populated through Stack Overflow, which is also not surprising. So this is some example code, and ultimately, if you have a path traversal and a name of a file inside of the zip, well, this will effectively follow it, right? So why do browsers use zip archives? So, for those who are familiar with Android, an Android APK is effectively a zip archive. So sometimes they use a zip upstream stuff to handle configurations and updates and whatnot. But the stuff that we're going to be talking about today is the use of these things called themes. And they are more popular in the alternative browsers where, obviously I want to change the theme of my browser to the background of Chuck Norris. If you want to do it, you can do it, you know what I mean? So these themes are pretty prevalent on alternative browsers, and for the most part, themes are handled in these browsers as zip archives. So if the browser does include themes, essentially they're going to be a zip archive. Like they may have a custom extension. Here's an example of the Beatty browser downloading a custom theme over HTTP, and its extension is BeatySkin. This is a zip archive. Anytime zip archives, for the most part, that I've observed that are used inside of Android browsers are always handled insecurely. Either they're downloaded over HTTP, they're written to the SD card, they're extracted from the SD card, and they're not validated for integrity whatsoever. So this has also been kind of beaten to death, but it's a great vulnerability class for Android browsers as well. So it's very trivial to man in the middle the download of a particular theme over HTTP and then basically inject your own malicious zip file and the response content. And if you include a path traversal attack, like in this example, then most of the time the browser is going to follow that and then write data to that location. I have some stuff up on GitHub. It literally takes less than 5 lines of Python to inject arbitrary data into a zip archive. It's really, really simple. So prepping your zip with a traversal attack just requires you to understand where the zip gets downloaded and written to, and then how far you need to get to something like the browser's data directory. So this primitive kind of builds an arbitrary write context, so either I can write new data into the browser's data directory, or I can overwrite existing data in the browser's data directory. And traffic injection can be easily done with man-in-the-middle proxy or man-in-the-middle dump. You guys are familiar with that. You can write Python scripts to your heart's content to do a lot of traffic manipulation with both of these tools. Here is an example. All the code is available on my GitHub, so you can download that and check it out. All the exploits too are available as well. All right, so now we have this arbitrary write primitive using this whole zip input stream vulnerability. So we need something specifically to target. So when an application chooses to build shared libraries in C and C++, they're usually done through the Android native development kit. And those libraries are typically stored in the application's lib directory, and it's owned by system. Now, developers can create shared libraries, and they can do whatever they want to them. They can mark them writable, readable, world readable, world writable, and then stuff them into applications, asset directories, which is the files directory when it's exploded and written to the device. So this is a non-standard way of creating executable code and then putting them into directories that aren't owned by system, that are owned by the browser. And this is what we want. These are the targets that we want for this arbitrary write primitive we can get through for parsing of zip archives. So prime targets, all 3 of these browsers have this. They are not the only ones. They are just the only ones that I could combine all the vulnerability classes to get code execution. But like the UC browser, Cheetah, I think those 2 browsers have writable code and non-standard directories. But again, this is the target, this is what we want to overwrite with this whole zip input stream attack. All right, so how do we analyze the attack surface? So initially when I went out and started researching all these browsers, I was looking at like 20 or 50 at a time on the Google Play Store, and I needed a way to just automate kind of consuming those browsers and looking for these vulnerable API implementations. So this is kind of the whole reason why I wrote Lobotomy. Lobotomy comes with something called a surgical API, and it specifically will go through and look for these vulnerable API implementations in the target browser. So it'll get you to the location and code, and that essentially for me sped up the process of I can manually identify whether or not a given vulnerability exists. So I apologize, screenshots are still pretty small. So this is the browser module from the surgical API. We're going to look for the parse URI method. Second screenshot, it found the parse URI method. Lo and behold, it's inside of the should override URL loading method. Top screenshot, it checks to see if the intent URI scheme starts with on that string particularly exists. If it does, it takes that intent object after it's returned from parse UI and it parses to something called resolve activity. That returns because the activity that we're targeting is internal to the app. And then the second piece here is that it calls it set component to nullify the component, but effectively you can bypass that with the selector attribute so this browser is vulnerable. So do we have the rest of our needed primitives for exploitation? We do. The read mode activity is private. Inside of its onCreate method, it takes the intent extra as a string web archive path and then assigns that as the first argument to load data with base URL. You can see here that the this.a instance is the reading mode view. And then again, in this context, it's hard-coded the meme type as text HTML. So now you can go through and actually do the whole JavaScript injection in the cookie database thing, but there's more. So the reading mode view, I didn't even talk about this because it's rarely ever seen, because it's so stupid. You should never, ever do this. So the reading mode view, it includes a special attribute called set allow universal access for file URLs. So whether or not JavaScript is running in the context of a file scheme URL, it can access content from any origin. So this literally means that you can just make like XML HTTP requests to like data on the file system, which if anybody researches browsers outside of this, you understand that that is a terrible idea. So attacking the Flinks browser, it requires a couple of things in order for us to set all this up. So we want to force it to download an HTML document to the SD card. Most of the time when browsers download stuff, they just write it to the SD card. So we need to do a little drive-by download attack to prep the SD card with our HTML payload. The next piece is we get the browser to load up another page with the intent scheme of use. And ultimately, we have everything that we need. So the extra that gets loaded up into load data with base URL is going to be the URL pointing to the SD card and our already pre-downloaded HTML. Now we're just going to load the cookie database inside of JavaScript because we can do that now with set allow universal access from file URLs. So this is a snippet of what this would look like. Here's the intent.html, which includes our URI abuse, and then you literally can just Google for this. It's pretty simple to regular exploit.html and then deal with your cookie data exfiltration via XML HTTP request. Statically, Lobotomy can also find instances of zip input stream as well. This is looking at the Maxon browser. It found a use for it. Maxon browser downloads all of its browser updates, like the app itself. It downloads it as an APK, it writes it to the SD card, then it unzips it from the SD card, and then tries to route it back to the data directory. And most modern phones will be like, fuck you doing? No, you can't do that. But it still tries to do it anyway. So this browser is vulnerable. Either you can just override the APK on the SD card, or you can man in the middle of traffic and backdoor, whatever you want to do. All right, so exploitation tails. So the Dolphin web browser, as you can already see, and I've already shown, provides theme files, a whole bunch of themes, actually. So the theme files, they were zip files with custom extensions. They were downloaded over HTTP, and they were written to the SD card, and they were effectively extracted, and then data inside of the theme files were applied to the overall browser, configuration, update, wallpaper, JPEG, whatever. We've already shown that the libdolphin shared library isn't stored in the browser's assets directory, and it is writable. So this is a prime target for using the zip input stream attack and then overriding shared code. Exploitation requires man in the middle of the theme download, very easy. So we inject a cracked theme into the HTTP response. It contains our path traversal attack. We override libdolphin, and then when the browser gets restarted, it'll load libdolphin on boot, and then it will be executing our code. I have a demo here to preface this. I'm on a Google Nexus 5. It's already rooted. I have an ARM compiled version of BusyBox. Netcat's on there, so for the proof of concept, that literally my executable code is just to call netcat and set up a bind shell. But obviously, you could be more creative, like Trojans, you know. All right, so we've opened up the browser, and then we're going to go to the themes page. We're going to download our new spiffy theme. Because who doesn't want a red rib theme for their browser? All right, so we've already done all of our injection and stuff like that. We got our man-in-the-middle dump, inline proxy script writing. Obviously, my phone is being proxied through this, etc. So we're looking for the, it's a .dwp file extension. Once we see that extension, we'll load up our own theme and then inject it into the HTTP response. A whole bunch of data. Okay, there we go. After the theme is applied, i.e. the zip contents are extracted, the zip archive thing works. It will effectively overwritten libdolphin. The browser gets restarted, and then now we can connect remotely to, remotely me being a stable network, to the bind shell that's running on the phone now. I'm the slowest typer, holy shit. All right, there you go. Thank you. Anybody running that browser in here right now? Okay, good. I mean, we're all on Chrome. That's not vulnerable. The Mercury browser was invulnerable to the intent URI scheme abuse. Actually, so the Mercury browser is literally vulnerable to everything that could be vulnerable to. It's got the, and it has a patch, and they're still pushing updates, which is really awesome. Also, too, for those who are wondering, not that I personally care, but I have tried to disclose this stuff, and I've just never, ever gotten a response, ever. So, the intent URI scheme abuse, it allows you to invoke this Wi-Fi Manager Activity 2 component. This component, it is private, and it basically enables this whole custom Wi-Fi transfer feature, which literally allows you to save and back up stuff from your PC, from the browser. But I don't really understand why they wrote this feature. So the Wi-Fi transfer features, literally, they spawn a web server, they host the SD card, and then they attach it to the network interface of the phone. Because why not? So I actually saw this and I was like, really? All right, so the web server's implementation, it contains directory traversal vulnerabilities in both the download and the upload functions. So because it's hosting stuff from the SD card, you literally can use a directory traversal vulnerability, and now you can just traverse, start reading and writing from the browser's data directory. All right, so that's really cool. Like, we can extract the cookie database, but there's more. So obviously, you want to be able to watch HTML5 videos in your browser, and Mercury said, I'll support that for you with a third-party library called, I don't even know how to pronounce it, Vimeo. So the Now Secure guys actually disclosed this a while back, but the Vimeo third-party SDK, when it loads an MP4, it will write shared libraries inside of the data directory and then mark them as like world-writable, obviously. So, like, we could exfiltrate all the cookie database, but because we now have this new context, we'll just use the whole upload path traversal vulnerability and we'll overwrite one of those shared libraries to achieve code execution. All right, so first we gotta get the shared libraries to be written to the data directory, so we'll download an MP4 file and then load it up inside of the browser. And then you'll see here that the initializer, the decoders were initialized, they're just writing all the stuff to disk. All right, so now we'll use the intent URI scheme abuse thing, and this will invoke the Wi-Fi transfer feature. Again, sets up a web server on the network. Yes. And then we've got our exploit here running. All right, I'm gonna pause this real quick. So literally what this does is it just pulls and says, like, immediately when the transfer feature is up and ready, I've got the network address, then kick off. So it knows now that the web server is there and it can use the path traversal thing to write. So it grabs the target IP, it takes our libd player shared library, it uses the path traversal thing, overwrites it on the browser's data directory, and that is essentially what the exploitation there is. All right, so we load up another video. It's not very reliable, I'm gonna be really honest with you. This shit crashes a lot. So it crashes, it doesn't even crash, it just hangs there for whatever, because now we're executing our own code. And then now we can connect to our netcat bind shell, and it looks like I'm still typing super slow in the terminal. There you go. My honest opinion, if you're using an alternative browser, don't do it. Popular browsers like Chrome and Firefox and Opera, they're significantly more secure. And honestly, it's just because they've had more eyes on them for a lot longer period of time. But once upon a time, all three of these browsers were vulnerable to this whole intent URI scheme abuse thing. So this exists everywhere. So I don't even cover half of the stuff that I found. So things like browsers, like obviously you want to watch Flash on your Android phone. So they'll implement Flash and they'll do it natively. Also other things like JavaScript interfaces. I'm pretty sure everybody's familiar with that. That stuff still exists. SQL injection into the content providers that hold all of your history and cookies. That stuff exists. Information leaks. I mean, it's all there. This is just the stuff that I felt was more important. But all this vulnerability still exists. Again, it's probably because none of these things have ever seen the light of day from a security perspective. But I would say, in general, if you're using any one of these three, that you are significantly more